Let's talk about momentum. Momentum is a property an object has when it's moving. It can be helpful to think of it as how much would something hurt if it hit you? The reason something hurts when it hits you comes from an object's tendency to keep doing whatever it's already doing. This is called inertia, which is the core principle of Newton's first law. When you get hit by something, the things that matter most are the object's mass and velocity. Let's take a look at a flying cinder block. Now, look at a football thrown with the same speed. The cinder block clearly has more momentum when it hits the grass. Something with a low mass, like a football, would need to be moving much faster to dig into the grass like the cinder block did. The cinder block, on the other hand, doesn't need to be moving fast at all to cause damage. Both mass and velocity matter. This relationship is written as P equals mv, where m signifies the mass and v signifies the velocity. Another way of writing this out is to say that momentum is equal to mass times velocity. This relationship is known as linear momentum. It's often what you think about if you see a collision, or it's commonly demonstrated by a Newton's cradle. Where linear momentum refers to objects moving in straight lines, a rotating object has angular momentum. Just as inertia causes objects to move in straight lines, rotating objects maintain their motion due to rotational inertia. Like linear momentum, angular momentum depends on two quantities: moment of inertia and angular velocity. This is written out as L equals I omega. Moment of inertia is analogous to mass, but there's a bit more to it. We can think of mass as an object's resistance to accelerating, or how hard it is to make something move. This is different when we're dealing with rotation. Moment of inertia depends not only on what is rotating, but where it's rotating around. This accounts for how difficult it is to start something rotating. Moment of inertia relates every part of an object's mass to its axis of rotation. This can be done in several ways depending on the system, but in its most general form, it's written as the integral over the mass of r squared dm. To simplify this a bit, we can look at a less complex system. In this system, we have 4 blobs of mass at different radii from the rotation axis. Here, we can replace the integral with a summation. Add up each mass and radius squared, and we get a value for the moment of inertia. The larger the moment of inertia, the harder something is to move. Take a throwing knife as an example. It can rotate about any axis, on or off the body. The moment of inertia is at its minimum when it's rotating about its center of mass. This means that the center of mass is the easiest place to get something to spin around. You can take advantage of this by holding it on end, and when it's released, you get a more controlled spin. So that's moment of inertia. This second term is angular velocity. It's represented by the Greek letter omega, where linear velocity, for things moving across a distance, is measured in meters per second. Angular velocity deals with circular motion and is measured in radians per second, or the measure of an angle over time. We've established two equations for momentum. Let's break them back down. P signifies linear momentum, and L, angular momentum. These represent both straight line and circular motion, respectively. M represents mass, and I, moment of inertia. V is the linear velocity, and omega is angular velocity. These two equations represent the same concepts in both linear and circular motion.